Hey guys, Mr. Betts here. I want to talk to you about something called a logistic growth model. And it's kind of similar to an exponential growth model, except it's a little bit more accurate at predicting what happens in the long run with certain types of situations. So if you think about an exponential model, it can only really accurately model a situation for some period of time. And then, like if we're looking at, say, population growth, resources are going to become limited. Population growth is going to decrease as a population gets bigger and bigger. So when that happens, exponential growth models fail for us. So we're going to look at a another kind of model. And so if you think about population growth, a population might go through a period that appears to be exponential, but it's going to hit a time when resources become limited, space becomes limited, and the population will start to level off. So with population growth, exponential models are not very good in the long run, and we are going to be able to use what's called a logistic model. This can also be used to model, say, the spread of a virus. So the spread of a virus may look exponential up to a certain time, and then the number of people who have not been infected might decrease, or mitigation measures might be introduced that start slowing the spread of the virus, and the total number of cases would start to level out. We might also see this with like the adoption of new technologies. So none of these follow a logistic model perfectly, but if you look at some of them, I'm going to just choose the refrigerator in here. If we look at the refrigerator model, when the refrigerator was first introduced, it looked like exponential growth. However, as you can imagine, we can't have more than 100% of people with refrigerators in their home. So after a certain period of time, the number of people getting refrigerators is going to start decreasing, where the adoption approaches 100%, but probably never quite gets to 100%. There are definitely homes in the world, or I should say in the US, that don't have refrigerators, but it's nearing 100%. So the logistic growth model, kind of like the exponential growth model, uses the fact that the growth is going to be proportional to the quantity, but it also is going to be directly proportional to some what's called carrying capacity minus the quantity. So this M right here, I'm going to talk a little bit more about that later. That's what's called a carrying capacity. It's going to be the maximum value of the quantity, or not necessarily the maximum value. We'll see some examples where it's not. But in the long run, the quantity is going to be approaching that value. So not only is the rate proportional to the quantity, but it's also going to be limited by this carrying capacity. So it's going to be proportional to the carrying capacity minus the quantity also. So for small y values, it is going to appear to be exponential growth. But then for larger y values, the derivative gets closer and closer to zero as the quantity gets closer and closer to m, and the rate will start to approach zero, and the quantity will level out. Using partial fractions and antiderivatives, we can get a general solution to this differential equation that looks like this. You do not need to recognize that general solution. You don't have to memorize that general solution. However, it does take into account this carrying capacity. C is going to depend on, it's not going to be exactly like we saw with exponential growth, but it's going to depend on the initial quantity, and then K is going to be some growth constant, kind of like what we saw with exponential growth, where a bigger K value will represent more growth or quicker growth. So let's look at solutions to this differential equation. I have, for a differential equation that models this logistic model, I have a slope field here. In that slope field, I've got a few things plotted. So the red curves are going to be solution curves depending on initial conditions. And the horizontal line here is going to be the carrying capacity. So you'll notice that growth for low populations starting at like A will appear exponential at first. So it's going to increase in growth as we get closer to the carrying capacity. But then when we get more than halfway from zero to that carrying capacity, then it starts to level out, and that carrying capacity is going to be a horizontal tangent. Notice that with an initial condition B, which is kind of near that carrying capacity to begin with, the growth starts out at its fastest right here and then starts to level off right off the bat. Notice also that if the initial population or the initial value is above the carrying capacity, instead of increasing toward the carrying capacity, it's going to decrease toward the carrying capacity. So it's going to get closer and closer, but it is going to be an asymptotic behavior. So the population or whatever we're modeling here will stay above the carrying capacity, but it's going to get closer and closer to it. So let's look through a few properties of this. I'm sorry, I want to look at a few examples of this first. So all of these differential equations model logistic growth, and they're all some version of this differential equation right here. And so one thing that we're going to want to know is when does, or what is the carrying capacity? So the carrying capacity, if the population is at the carrying capacity, we will see zero growth, meaning that the population or the value is not changing. So we can set the derivative equal to zero. So to get the carrying capacity here, we can set the derivative equal to zero, and we're going to get two solutions. We should always get one solution when the population or the quantity is zero, but we're going to get another one here where this is equal to zero, or the population is 35,000. So the carrying capacity obviously is not going to be zero, but it's going to be this 35,000 here. The second one, we get the same thing. If we set this equal to zero, then we get a carrying capacity, not zero. Okay, so zero is not going to be the one, but it's actually going to be 180,000. Or is it 18 million? No, 180,000. So that's going to be the carrying capacity for this model here. This one, if we set this equal to zero, we get solutions at y equals zero, but then also where 10 minus y over 60 is equal to zero, and that's going to be at 600. So that 600 would be the carrying capacity. So if we're given a differential equation that models logistic growth, we set that derivative equal to zero, and that will give us our carrying capacity. The fastest growth will occur at half of the carrying capacity. So if we look at this graph right here, if we want to know when the population is growing the fastest with an initial condition here, let's say the carrying capacity is, say, 5,000, and the initial population is, this looks like it might be about 500. The population will grow faster and faster and faster all the way up to this point right here, which is half of the carrying capacity. And then it will, the rate will start decreasing, which means that the fastest growth will occur at a population of 2,500. If we wanted to maximize growth, we could do that by taking a second derivative and looking at where that changes from positive to negative. We could also look at a graph and see where the graph changes from concave up to concave down. But with a logistic growth model, we know that it's going to be half of the carrying capacity. So it's just a simple arithmetic operation. We just take the carrying capacity and divide by 2. That's all you need to do. I need to go back to this. I do want to look at other solutions here. If the population starts out at, say, 4,000, I don't know exactly what that is, but it looks like it could be about 4,000. It wouldn't make sense that if we said that the population starts at 4,000, but the fastest growth is at 2,500. So if we're looking at fastest growth for a population model that starts above that level of fastest growth or above half the carrying capacity, then the fastest growth will happen right at the beginning, because the growth represented by the slope of the curve is decreasing and getting closer and closer to zero as the population approaches the carrying capacity. So if the value is not in the range for the solution, if 2,500 is not in the range for the solution, meaning that it's not between 4,000 and 5,000, then the fastest growth will be at the beginning when t equals 0. Same thing is true. The fastest change, so not really growth, but decrease, So the population will be decreasing the fastest initially if the population is above the carrying capacity. Okay, another thing to look at, just looking at the graph of the solution. The solution curve will always be concave up for values below the fastest growth, and will always be concave down for values above the fastest growth, as long as we're below that carrying capacity. If the initial condition is above the carrying capacity, then the function will be decreasing and concave up, approaching that carrying capacity. Also, since the concavity changes from up to down at that point of fastest growth, then this right here will also be an inflection point. So if you are asked where a graph of a logistic growth model has an inflection point, then we just want to figure out what the carrying capacity is, divide that by 2, and at that point we will have an inflection point. I mentioned this already, but if the initial population is greater than the carrying capacity, then the solution will approach the carrying capacity from above. It's important to understand that we wouldn't expect it to go below the carrying capacity and then approach from below, because that doesn't, as you can see here, it doesn't match the slope field for the differential equation. We would expect a slope of 0 here, so the function cannot cross over that slope of 0. One last thing, the range of values in the solution curve will include the initial condition and go to but not include the carrying capacity. So what that means is, if, say, the carrying capacity is 5,000 with an initial population of 1,000, then the population values will range from 1,000 to 5,000 exclusive. So the range of solutions, or the range of values, will not ever actually get to 5,000. It's just going to approach it because of that asymptotic behavior. But it will equal 1,000, so it will take on all the values in between. If the initial population is, say, 4,000, then the range of values will be 4,000 to 5,000, including 4,000 but excluding 5,000. Now, if the population starts above, let's say this is 6,000 here, then the range will be starting at the lower value, 5,000 to 6,000, including 6,000. So it starts at 6,000 and starts decreasing, but when we write our range in interval notation, we start at the lower value, so it would look like that. So the range of values in our solution curve will include the initial value and then go to but not include the carrying capacity.